Hello students, welcome to the session. In the previous few sessions, we are discussing about the flip-flops and latches. We already know that there is a small difference between latches and flip-flops. Latches and flip-flops, they are going to store one bit of information. These are called as the storage elements. But there is a slight difference. So latches, generally they will have the asynchronous inputs, but flip-flops they will have synchronous inputs. Okay, so they are level triggered and these flip-flops are edge triggered. We started our discussion with the SR flip-flop. SR flip-flop has got an indeterminate state or it is invalid state. So in order to overcome that, we go for the next type of flip-flop, which is the JK flip-flop. And in JK flip-flop also we have the race around condition, because the output is going to change from 0 to 1 or 1 to 0. So continuously it is happening. So in order to overcome that one, we are going for the next type, which is the master slave type. So now those are the types of the flip-flops. Now we'll continue our discussion of the flip-flops in order to see what is a D type of flip-flop as well as the T type of flip-flop. So we have overcome the disadvantages of the JK and the SR flip-flop by using the master-slave configuration. Now this master-slave JK flip-flop, with a slight modification, we are going to get the other types of flip-flops, which are called as the D as well as the T flip-flop. So how to convert a JK flip-flop into a D flip-flop? So a D flip-flop, it is obtained from a JK flip-flop itself. So by connecting J, so the input, it is connected directly to the J terminal, but K is fed through an inverter. So that type of configuration, it is being shown over here. See, if D is equal to 0, then its working is like this. If D is 0, then we are getting Q as 0. Okay, so here it is being shown. If D is equal to 0, output is 0. That is Qn plus 1 is 0. So how we tell the output of the flip-flops is that it is the previous state and the present state. So in our discussion, we have already seen that Qn represents the previous state and Qn plus 1 represents the present state. So here if D is 0, output is also 0. So the present state, it is 0. So if D is 1, output is 1, then we'll get the Qn plus 1 as 1. Okay, so this can be constructed, the JK flip-flop, using NAND gates over here. So this is the construction, this is the logic diagram of the D flip-flop, wherein D, the input is directly fed to the J terminal, but it is fed through the inverter. We know that we could realize NOT gate using the NAND gate. So one NAND gate is being provided over here, so that here it is complement of D, that it is coming over here. So we'll get the K input, and this is nothing but our JK flip-flop. So this is the truth table. So in this truth table, you could see that whenever clock is present, at that time only we are getting. So if D is 0, then we'll get Qn plus 1 as also 0. If D is 1, we are getting Qn plus 1 also as 1. Okay, so if there is no clock signal, means it retains its previous state. Okay, so this is how we can explain the D flip-flop. Now let us move on to the T flip-flop. So T flip-flop is obtained by shorting J and K terminals. That means J and K, they are connected together to our input, which is the T input. So this is the logic diagram, and here we could see that this is the truth table. So in this truth table, you could see that if the T is 0, then we'll get the present state as previous state only. Okay, so our Qn plus 1 is the present state, Qn is the previous state, so it will retain the previous state. So if T is equal to 1 means, then it will toggle. So that means if Qn was 0, then the present state becomes 1. If Qn was 1, the present state becomes 0. So that's why it is being represented here as for T0, we are getting Qn. What is Qn? It is a previous state. So the present state is equal to the previous state. Here you could see that if the previous state was 0, now we are getting it as 1. If the previous state was 1, we are getting the present state as 0. So this is nothing but Qn bar, or it is toggling that is going to happen. So this is what, and these D and T types of flip-flops. So why we have discussed is they find it's their usage in the construction of the memories. There we are going to use is D and T types of flip-flops. Okay, so the next topic that we need to have to discuss is the application of the flip-flops. Mainly there are two applications of flip-flops. One is register, the other one is counters. So these are the very important applications of the flip-flops. So flip-flops, you know that flip-flops can also be called as binary cells, and these binary cells, they are capable of storing one bit of information. So a counter, it is nothing but a group of flip-flops which are connected together. But here shift register is also a group of flip-flops, but the way we connect is slightly different. So a collection of flip-flops in cascade, we can call it as a register. So it can be used to store the information in the digital form. Okay, so there is a cascade of 4 flip-flops. So it can store a nibble of information. So for a 4-bit register, we know that we could store the information from 0000 to 1111. So I have already informed you how to write the binary table. So with 4 bits, we'll get 16 different combinations. So all those 0 to 15, we can store in this 4-bit register. So a register is, it is nothing but a collection of flip-flops. Okay, so that is called as a register. First, now let us move on in order to see what is the meaning of a shift register. So shift registers, it is the, it will store the binary information. So this binary information that is stored in the register, it can be moved from one stage to the other stage, and this is done within a register. So within a register it is done, and in order to do that, we have to apply the clock pulse. Okay, so the binary information in the register, it can be moved from one stage to the other stage, and it is within the register. So how we transfer that information is by the application of the clock pulse. So a shift register, it is capable of moving or shifting the data that is stored in the flip-flops in both the directions. So such flip-flops, such shift registers, they are called as bidirectional shift registers. If the shift registers cannot transfer the information in both the directions, then those shift registers are called as unidirectional shift registers. Now it is time for us to see the types of shift register, and this type, it is based on the shift direction capabilities. So first, let us see the serial in, serial out. So the operation that is performed, it is called as SISO. That means serial in, serial out. So data bit is given over here. So only 3 bits have been shown. It is for illustration. You can assume or you can construct a shift register of any number of bits. So here, just for information and illustration, a 3-bit shift register is being shown. So a data is being fed in one direction, so it moves on to the next one, and it comes out from the last shift register, last flip-flop. So this is the direction of movement of the data. So these flip-flop, these shift registers, they are called as shift right operation that they are performing. So we could see that there is one more example in which data is fed from this side and it moves towards the left and it comes out of the last flip-flop over here. So this kind of shift, it is called as as by the name, we could say that it is left shift. So here in this case, what happens is data is set serially, okay, data is fed serially and it is taken out serially. This operation, it is called as serial in, serial out operation. Now we'll move on to see the second one. This is serial in, parallel out. So actually feeding the data to the shift register, it is done in the serial manner. That means serial manner in the sense one after the other, the bits are fed to the shift register. Once all these bits in the shift register, they are fed, then it is taken out at once. This is called as serial in, parallel out. Okay, so this operation, it is called as SIPO. Now let us move on to the third one. This is called as parallel in, serial out. So in one clock pulse, data is fed to the shift register. So this is the direction of data that is fed, and the data is taken out serially. Serially in the sense it is one bit after the other bit, the data will come out of the shift register, and this is called as the parallel in, serial out, or it is in short, it is called as PSO. Now let us see the last one, which is the very efficient one, which is called as the parallel in, parallel out shift register. And this parallel in, parallel out shift register, it is the most efficient one because we are feeding the data in parallel and taking out the data in parallel, and this could be done within a single clock pulse. But they require more number of clock pulses, which we have discussed the previous ones. They require more number of clock pulses. Now, how many clock pulses are required in order to see that? At least we need to have to see one of the shift registers so that we could get an idea how many clock pulses are required in order to feed the data or in order to take out the data that is present in the shift register. So here there is one example, that is 4-bit serial in, serial out shift register is being shown. So here the operation that is done is SIPO, that is serially data is given inside and parallelly it is read. Okay, so this particular 4-bit shift register, in order to perform serial in, parallel out, it requires 4 clock pulses. Okay, how it requires 4 clock pulses, we are going to see that. So if it is n bits means if you have n flip-flops of this kind, then it requires n clock pulses. Okay, this is a 4-bit shift register, and this shift register is going to employ using D flip-flop. So this is called as the data flip-flop, or it is called as the D flip-flop. D flip-flop is also, it is a data flip-flop. So now we have the 4 flip-flops that are used over here. So these flip-flops, they are DA, DB, DC as well as DD. Okay, and QA, QB, QC, QD, they are all the outputs, and here clock is given in this manner. So the meaning of this is all these flip-flops will be simultaneously clocked. Okay, so the meaning of simultaneous clocking is that every flip-flop will get the clock at the same instant of time. This is a 4-bit serial in, parallel out shift register. So in order to perform this serial in, parallel out shift register, so now first data is fed in the serial manner. So in order to feed the data in the serial manner, how it is done is, here we have QA, QB, QC, QD. They're all the outputs with QA as the most significant bit. So what we are trying to feed this shift register is, we are trying to put the data 1011. Okay, so this is the data that we need to have to put. So in order to put this, we require 4 clock pulses. How it requires 4 clock pulses? Now let us see. Here, you should not confuse the data with data and how it is fed to the shift register, because here 1011 is our data and we need to have to feed the data starting from LSB. LSB is what? It is the least significant bit. So now look at the truth table for it. So in this truth table, you could see that after the first clock pulse, the serial data that is given, here is the serial data that is given. So the serial data that is given is the least significant bit, which is 1. Okay, so the output of the shift register, what will be QA? So after one clock pulse is given, okay, so that whatever the data that we give for the first one will appear at the output. So when we feed 1 in the serial data input over here and apply 1 clock pulse, so whatever the data that is available over here will appear at the output of the first register, first flip-flop. Okay, so that's why we are getting the output as QA as 1 and rest of them they are on zeros, because now after the first flip-flop the output is available only at QA, that is the first flip-flop it is available. Now we need to have to feed the second bit. I think you are all aware what is the meaning of parallel as well as the serial. Serial information is we are feeding it bit by bit. So we have fed the first bit now. Now we need to have to feed the second bit. So when we feed the second bit over here, okay, here also 1 bit is fed and QA, it is the output of the first flip-flop. It goes as input to the second flip-flop. So thereby here the data that is given is, here also it is 1 and here also it is 1, right? So thereby that is getting shifted over here. So that shift is being shown over here. That means output of QA, it comes out of B now. Okay, so whatever was available in QA, now it comes at QB now. So it is getting shifted and you could see that. Okay, so here 1, it comes over here. Okay, so this one, it comes over here. So after that, it is going in this direction, it is shifting. Okay, then our second bit, it will occupy the first flip-flop. Okay, so thereby after the application of 2 clock pulses, we'll have the output QA as 1, QB as 1, this is QC and QD as 0, 0. Okay, so till here that you need to have to see. Now let us move on in order to apply the third clock pulse. So before applying the clock pulse, we are supposed to give this data over here. What is our data? Our data is 0. So that data 0 is given over here and we apply 1 clock pulse. So when we apply clock pulse, what happens is, so the available data over here will appear at the output. But initially there was 1 over here. So that one will appear over here and QB was also 1. That one will appear over here. So thereby the outputs of these flip-flops, it will be QA is equal to 0, QB is equal to 1, QC is equal to 1 and QD as 0. So this is the output of the shift register after the application of 3 clock pulses. Okay. So now let us feed the last bit. So in order to feed the last bit, it is 1. So the data is given over here. Okay. So that data is given. So how is the data? Now data it is 1 over here. Here the input is 0 and here the input is 1. Here the input is 1. So when we apply the clock pulses, okay. So when we apply the 1 clock pulse, then 1 that is available, it will come out of this. This 0 will come out of this. This 1 will come out of this and this one will come out of this. Thereby we have the data 1, 0, 1, 1. That means what? In serial in parallel out, we require a minimum of 4 clock pulses in order to feed a 4-bit shift register. Okay, so that explanation is being given over here in this. So you could see using the timing diagram also it is being given. So during negative edge of the clock pulse, the change is taking place over here. So QA will be enabled for 2 clock pulses and then it goes 0 and 1. This is the QA output and this will be the QB output because it will data appears through it after 1 clock pulse. So that's why it will change its state during the negative edge of the second clock pulse. So thereby QB is 0, 1, 1, 0. The same thing applies to QC as well as QD also. Okay, so just now we have seen 4-bit shift register. Okay, so with the data 1011, we have performed the task that is serial in, parallel out. Okay, so now if we want to perform the operation serial in and serial out. Okay, you assume that we want to do this operation that is serial in, parallel out. So in order to perform this serial in, parallel out, we require 3 more clock pulses. Okay, so why it is 3 more clock pulses is that we are taking the output at QD. Okay, so after this particular thing is what? This is serial in, parallel out. Is it not? So this is serial in, parallel out. So for serial in, parallel out, we use 4 clock pulses so that the data available is 1011. Now if we want to do an operation of serial in, serial out. So if we want to do serial in, serial out, then what we need to have to do is we were taking the data at QD. Okay, so that data must be available at QD. So in order to get all 1 bit by 1 bit, it is available at the output of the 4th flip-flop. So we have already got 1 over here. Is it? Still 3 more bits that we want. Those 3 bits can be obtained by the application of 3 more clock pulses. So thereby we need to have to read the data in this manner, that is 1011. That means in order to perform serial in, serial out, serial in, serial out operation, we require 7 clock pulses in order to do this particular operation. Okay, so we have seen the serial in, parallel out. So that is the first one that we discussed. So serial in, parallel out requires 4 clock pulses. This is particularly for 4-bit shift register. So if you are taking more number of bits in the shift register, then you need to have to tell accordingly. Here it is 4-bit shift register. So thereby, in order to perform serial in, parallel out, we require 4 clock pulses. So if we want to perform serial in, serial out, then 3 more clock pulses are required. So why it is not 4 is that, so after the application of 4 clock pulses, we have already got this 1 at QD. Okay, so this is the least significant bit is already available for us. So rest of the more significant bits that we need to want to have, so they can be obtained by the application of 3 more clock pulses. So that's why we require 7 clock pulses for performing this serial in, serial out operation. So I said in the beginning itself, it is how many clock pulses for parallel in, parallel out. So for 1 clock pulse, we load the data. So all the data that will be available. So thereby parallel in, parallel out operation, it requires only 1 clock pulse. Then last one is here it is, we have not discussed about it. This is parallel in, serial out. Okay. So this case first thing is we need to have to load the data. So if we load the data, for that one clock pulse will be taken. So when we apply the data or when we load the data in the shift register, that is when we do this parallel in operation. So for that, one clock pulse will be used. So when we do like this, one bit is already available for us. In order to get rest 3 bits, we require 3 more clock pulses. So that's why we must be very careful while doing this one. So here, why this piezo operation, that is parallel in serial out, is taking 4 bits is that first one for loading the data. So when we load the data, 1 bit is already available and we want the rest 3 bits. So thereby it is being shown as for the piezo operation, we require 4 clock pulses. Okay. So this is last single small definition which is being written. So what is a shift register? It's a cascade of flip-flops. So cascade in the sense one after the other, the flip-flops are connected. So they will share the same clock. So I have already shown you they are going to share the same clock. That means what here it is. So that means clock signal is simultaneously given to all the flip-flops. Okay, that is what is the meaning of that. Okay, so that's the meaning of same clock pulse. So in which the output of each flip-flop, so every flip-flop output, it is connected to the data input of the next flip-flop that is in chain. So this is going to result in a circuit that is going to shift by one position in the bit array that is stored in it. So after the every transition of the clock pulse, that means what data is getting shifted to the next flip-flop. So that is how we are going to construct the shift register. So finally we could see that this is a 4-bit shift register. So with respect to 4-bit shift register, we require these many clock pulses in order to perform these 4 types of operations on the shift register. Thank you, students.